Hey guys, sorry I'm not there today. In this video, I'm going to go through the content for exercise 5.4, which is all around walks, trails, cycles, paths, and circuits. So these are basically ways to just move around a graph. So if you think about your graph as a road network and your vertices as towns, this is ways to get around your graph. So this is what's called a traversable graph. Traverse just means that you can move around. All right, so in your books, can you write that heading for me? Walks, trails, paths, circuits, and cycles. Underneath that, the handout that you received today from your teacher, you can stick that in. A lot of the content today will revolve around that. All right, so just quickly, the learning intentions and success criteria. So basically, the skills that you need to learn today is to distinguish between the different ways of moving around a graph. So that's your walks, trails, paths, circuits, and cycles. Then you can be able to identify those and highlight them in a given graph. After that, we are going to look at what's called Euler circuits and Euler trails and how they differ from our standard circuits and trails. And we'll go through a couple of shortcuts on how to identify those in your graph as well. And please, anyone, pause this video at any time if I'm moving too fast. All right, so this is all in that handout, so you don't need to write it down, but I will just give you a quick explanation on each one. So a walk is essentially any movement through a graph. So if in this diagram here, if I'm moving from gate 1 to the bridge, that's a walk. If I then move to the fern gully, that's also a walk. So a walk is really just the umbrella term here. It's any movement through your graph. It connects two vertices or more, and it can be done in any order. So any movement is a walk. A trail is a type of walk. However, in a trail, we can't repeat edges. We can repeat vertices, but we can't repeat edges. So if I go from gate 1 to the bridge, I can't just go back to gate 1 because I would be repeating that edge, and it's now no longer a trail. A trail, doesn't matter how long or short it is, it simply cannot repeat edges. So in the example here, we go from gate 1 to bridge to fern gully, down to gate 2, to the old tree, to the waterfall, to the bridge, to gate 2. So you'll notice in there, we did repeat a couple of vertices. We repeated the bridge, we repeated the gate 2. However, we did not repeat the edges. A path is similar. However, in a path, we cannot repeat any vertices whatsoever. So in the example here, we've gone from gate 1 to fern gully, to bridge, to waterfall, to the old tree, to gate 2. So from there, I couldn't go anywhere else because I can't go back to the fern gully because then I'm going to repeat that vertex, and I can't go back to the bridge and I would be repeating that. So a path is a type of walk where you cannot repeat any vertices. A circuit is a type of trail that begins and ends at the same vertex. So like a trail, you can't go over the same edge, but you can repeat vertices. So a circuit is a type of trail that starts and ends at the same vertex. So you finish where you start. So again, in the example here, gate 1 to fern gully, to bridge, to waterfall, to the tree, to gate 2, to bridge, back to gate 1. We started where we finished where we started, and we did not go over the same edges. So no repeated edges. A cycle, that's a type of path that starts and ends at the same vertex. So in a path, you cannot repeat the vertices. However, in a cycle, you can repeat the first and last vertex. They can be the same. So cycles and circuits are very, very, very similar. In this example here of the cycle, we've gone from gate 2 to bridge to waterfall to tree, back to gate 2. You can see that there with the red arrows. So apart from the first and last vertex, we haven't repeated any at all. This is just a quick little summary for you. So a walk with any movement from one vertex to another, no restrictions or anything. That's the umbrella term. Trail, you move from one vertex to another without repeating any edges. A path, we move from one vertex to another without repeating edges or repeating vertices. A circuit, we start and finish at the same vertex. Repeated edges are not allowed. Cycle, start and finish at the same vertex. Repeated edges aren't allowed. Repeated vertices also aren't allowed apart from the start and finish. And this table you have in your notes there. So again, it's just a nice summary of what's allowed and what's not allowed in our different types of movements. All right, so what I'm going to get you guys to do is just in your notebook there. In a minute, I'm going to pause the video, but what you need to do is try to draw both these shapes without lifting your pen off the paper and without retracing any lines. So as soon as that pen's on the paper, you start drawing, can't lift it, and you can't repeat any of your edges. So pause the video now, try and draw these two in your books without repeating any edges or taking your pen off the paper. All right, so hopefully you've had a go at that. In this case, they are both possible, which makes it nice and easy for us. So in the first one, there's a couple places you could start. Go from D to E, over to B, down to C. We could go up to E, to A, to B, down to D, to C. So in this case, that one's possible. There's a few different ways it can be done. I have repeated vertices, but that doesn't matter. I haven't repeated any edges. The second one is also possible. Again, there's a few ways it can be done. I could go from E to A, over to B, down to F, down to D, over to C, up to E, across to F, and back over to E. So yes, these are both possible, and there's a reason I'm showing you this. So these are what's referred to as an Euler trail and Euler circuit. So just a quick reminder, in a trail, we can't repeat edges. A circuit's the same, except we have to start and finish at the same vertex. I'm going to get you to copy this down. So an Euler trail is a type of trail, but we use every single edge in the graph. So this first one, we just did an example of an Euler trail. We finished at a different vertex, but we crossed every single edge exactly once. So an Euler trail is a type of trail. We don't repeat edges, but we include every single edge inside of our graph. There's a little bit of a shortcut here to be able to do this, or be able to work it out if it actually exists. It's possible if there are exactly two vertices with odd degrees. So if I look at this first one here, vertex A has a degree of 2, vertex E has a degree of 4, B has a degree of 4, C has a degree of 3, so I'm freehanding this and it's a bit tricky, and D has a degree of 3. So in that graph, there are exactly two vertices that have an odd degree, therefore an Euler trail is going to exist. So that's a way to determine if it exists before we actually have to try it. So it's not just, trial and error and we'll keep trying to work it out. We can tell that there is going to be one. And as a little bit of a shortcut or a hint, an Euler trail will always start at one of the odd vertices. So when you drew yours just before, you might not have noticed, but all of you would have started at either D or C to make it work. If you started at A, E, or B, you wouldn't have been able to do it. And often if it's asking for the Euler trail, the way we would write it is we'd go, all right, so the Euler trail here, starting at D, and then it doesn't matter really which way I go. I could go to E, and then up to A, and then I'd write the whole thing. I'm not going to do that, but I'd go D to E to A to B to C, E, etc. like that. So when we actually write out the Euler trail, we write out the vertices like that. Then with an Euler circuit, it's very similar. We need to finish at the same vertex that we started at though. The shortcut here is all vertices are of even degree. And same sort of thing here, we have to cross every single edge. So that's what defines an Euler circuit. Every edge is used exactly once and we start and end at the same vertex. And all vertices have to be even for this to work. So looking at this one, B has a degree of 2, A has a degree of 2, D has a degree of 2, C has a degree of 2, F is 4, and E is 4. So all vertices are even, therefore an Euler circuit will exist. So often a question will be like, here is this, does the Euler trail exist? If so, write it out. So firstly we do this, look at the degrees. If they're all even, yes it exists, and then we can list it out. This one we could go from E, A, B, F, D, C, E, F, E. So make sure that's written down. This is very, very important. If you need to pause it, please do. And lucky last thing that we'll do here is we can just look at these graphs. These are the questions I was just talking about. So write these down in your book, A, B, and C. I want you to have a go first. So for each one, first determine if it has an Eulerian trail, Eulerian circuit, or neither, and state why. And then if the graph has an Euler trail or an Euler circuit, show one example. All right, so pause the video now, spend 5 or 10 minutes working these out, and then we'll go from there. All right, so hopefully you've had a chance to do that. So the first one, in these ones, the vertices aren't labeled. Normally they are, so we'll probably just have to do that ourselves first. So I'll say that one's A, B, C, and D. Doesn't matter which ones you label. All right, so in this first one, A has a degree of 2, B has a degree of 2, C has a degree of 2, and D has a degree of 2. So what that tells me is that an Euler circuit exists in here. And look, every Euler circuit is also an example, really, of an Euler trail. So they both exist. Here, one of the examples could be going from A to D to B to C back to A. There's quite a few examples. You could start at any of the vertices on that one. So yes, both circuit and trail exist for that one. For B, first one has this one up here has a degree of 2, 2, 2, 3, and 3. So what does that tell us? Well, that tells us that in this one an Euler trail exists, but not an Euler circuit. We have 2 odd vertices, therefore an Euler trail. Last one. This one has a degree of 2, degree of 3, degree of 3, degree of 3, and degree of 3. What that tells me about this graph is that neither exist. We have 4 odd vertices, which doesn't satisfy the conditions for an Euler trail or an Euler circuit. We need exactly 2 odd or even. You can have a crack if you really want to see if you can find an Euler trail or an Euler circuit in that one, but it does not exist. All right, guys, so that's it for today's content. What you can do now is have a crack at 5.4. All the questions are on Compass and all the resources and everything. If you haven't finished 5.2 or 5.3 yet, you can also catch up on those. Good luck.